each of these 3 test tubes, I've got some aqueous copper-2 sulfate solution, which we met before as having the formula CuOH2O 6 times 2 plus Aq. I'm going to demonstrate what happens when we add dilute ammonia to this sample. Now, importantly, I'm adding an excess of dilute ammonia to this sample. So I'm going to add dilute ammonia and shake, and keep adding and shaking like so. So we get a really nice change of colour to a deep blue solution is the textbook description, normally a deep blue solution. Now what happens with this CuH2O 6 times when it forms this deep blue solution is that some of the ammonia ligands, and it turns out 4 of those, 4NH3AQ, replace some 4 of those water ligands to make something which looks like this. Oops, H2O twice. Now, ammonia is not charged and the water is not charged, so the overall charge on that complex ion continues to be 2 plus. But because we need to balance this equation, there's another 4 water molecules which are removed from that complex ion like so. So in this example, this is a so-called ligand substitution reaction, and the identity of the ligand has changed and the colour has changed. So the identity of the ligand can affect the colour of a particular complex ion. This complex ion, then the new one over here, CuNH3 4 times H2O twice, if I just sketch this out, it looks something like this. So 4 ammonia ligands tend to go around the axis like so, sorry, around the equator like so, equatorial, and 2 waters on the axis like that. Noticing again that the atom within each ligand which forms that dative covalent bond, so the one with a lone pair of electrons to form that dative covalent bond, is pointing towards that central metal ion each time. So this substance here is the product of that reaction. Again, in this example, we've got 1, 2, 3, 4, 5, 6 dative covalent bonds forming to that central metal ion. So this is a coordination number of 6. And the shape around that particular complex ion is again octahedral. So notice this stuff here is the deep blue solution, and the cause of that colour change is swapping the ligand identity. Now, there's a second ligand substitution reaction involving that CuH2O6 2 plus, this time with some concentrated hydrochloric acid. So I'm going to do this bit in the fume cupboard. So I'm going to take this original sample of the copper sulfate and come into this fume cupboard and just add an excess of this concentrated hydrochloric acid and a couple of a couple of drop-in pipets of that one like so. Now this one here, hopefully you can see, is yellow in colour. It might look a little bit green, and that might be because there's a little bit of that blue solution still left over, but it's a yellow complex this time. So I'm going to take all of these and pop them into that fume cupboard now to avoid the fumes from coming out from that concentrated acid. And let's have a look at what's happened with the concentrated hydrochloric acid. Now in this example, we started again with the hexa-aqua copper-2 ion, the copper-2 ion with 6 waters attached to it over here. And this time I did an excess of concentrated hydrochloric acid. Now we use concentrated hydrochloric acid because that's a really good source of chloride ions. And in this case, 4 of those are at work. So 4 chloride ions working here. Moving across this time, the new complex is CuCl4 times. So it's different this time. The coordination number has changed. And the overall charge, we started with a 2 plus and we've got 4 minuses here. So the overall charge on that complex ion becomes 2 minus Aq. And we need to balance that equation. So 6 waters need to go on this side of the equation like so. Now this time we've got Cu with 1, 2, 3, 4 bonds forming. So Cl on the end of each of these. Cl here, Cl here. Overall charge is 2 minus Aq. That substance is yellow. It has a coordination number of 4. And this time it is a tetrahedral complex. So the shape around that central metal ion is tetrahedral. So notice this time we've changed two things. So we've changed the identity of the ligand, but also the coordination number. So both ligand identity and coordination number can influence the colour of a transition metal complex. Notice also that just by swapping chlorides for waters, we've changed the coordination number and changed the shape of the complex. And the reason for that is reasonably straightforward. A chloride ion, Cl-, even though it sounds smaller than H2O, water molecule, chloride ion is much bigger than a water molecule. And therefore we can literally only fit 4 chlorides around that central transition metal ion. So this time we've swapped smaller uncharged ligands for big charged chlorides. And when that happens, we can get a change in coordination number. In this case, the bigger ion and the fact that they're all negatively charged and repel each other as well helps to make sure that this complex ends up as tetrahedral in shape instead of octahedral for the CuH2O6 2+ ion.